Hey team, in this video we're going to look at component 4 of the Unit 1 practice SAC on polynomials, relations and functions. You can see it's laid out here, and I've actually already graphed the function with its given domain on the right. So the function being this. Okay, 2x plus 5 on x plus 1. And we're asked to make a new function of this form. So hopefully you recognize that that's a hyperbola, the new form that we need to have. So if we think it's going to be something like that. But we have some requirements to meet. We have to have a between -5 and 10. We have to have b between 0 and 10. The slope has to have an initial height of 3 meters. So that's a really important fact that we need to realize, that our line needs to actually come through 0,3 like so. We can't leave our asymptote on the vertical axis, which is actually already natively happening for us. We can actually see, because of the x plus 1, we have an asymptote at x equals -1. So from there, we need to have slide has a final height g of x, so our new function is called g of x, between 1/4 and 1/3. So over here, our final point at 8, needs to be between 1/4 and 1/3. So either on the low end 0.25 or at the high end 0.333, repeated somewhere in this range is what we need to do. And the slope is approaching 0 when the slide ends. So we can't have, for some reason, really straight. We don't want it that. We want that hyperbola sort of shape where it's flattening out. So we need to design something, some hyperbola function that meets that requirements. As part of this task, you need to write a function that meets the requirements, or as many as possible. Include a description of how you approach the task of finding the equation and what techniques did you use. Include a sketch of your equation over an appropriate domain. Well, that's an appropriate domain there. And do you meet all the design criteria? Show if it does or doesn't. And that's a really important bit. Showing, okay, is how do you meet that requirements? In particular, this sort of one at the end, a little bit of thought needs to be put into how do you do that. So there's a couple ways you can go about this problem. The first is, and the really neat way, is to realize that up here is also a hyperbola that currently has an endpoint. If we do a comparison graph, so currently we're going through 0,5. Okay. And sometime later we are at 8, and if I do I want to calculate ycalc at the x value. So at 8, the y value is actually 2.333. So 2 1/3. And that's our current function. And if we remove the domain off this graph, you would see that that is actually a hyperbola. But if we go to the equation, and what we're trying to do is, surprise, surprise, we're trying to go from 0,3 to 8, 1/3. And if we notice, both the y coordinates have actually just been moved down too. So if we recognize that I'm going from 0,5 to starting at 0,3, and my current function ends at 2 1/3, and I want to end at 1/3, both those points have just been translated down 2. So we could just apply a vertical translation down of 2 of that, because this equation can be rearranged into this form. So let's have a look at that first. So we know f of x is 2x, was it plus 5? Yes, on x plus 1, which can be written as 2x plus 1. The reason why I'm putting the x plus 1 is because that's the denominator. So if I expanded that, that's going to become 2x, and that's going to become 2. but I actually need a 5, so I need to write a +3 on the end. And I can rewrite this as 2x plus 1 on x plus 1 plus 3 on x plus 1. I can always split any fraction in the numerator an additional positive as long as I keep the denominator the same. And that allows me to cancel that and that, which leaves me with 2 plus 3 on x plus 1. So we can read it as 3x plus 1 plus 2. Now that's the current original function. That's this one. Okay. Now if I want to turn that into this right-hand one, which does meet the requirements, okay, it starts initial height of 3, it's ending at a third, perfectly at a third, which is in the include, and the slope is getting flatter, as we can already see from our picture on the calculator. We're just moving that graph down. Okay, I need to translate this down by 2. Okay, so to do that, we want g of x to equal f of x take away 2, which is going to be 3 on x plus 1 plus 2, take away 2, which is going to be 3 on x plus 1. Now, it doesn't quite look like it, but it does meet our requirements of the b on x plus 1 plus a. In this case, though, b is equal to 3, and a is actually equal to 0. We could write it as plus 0, and that's fine. And that, taking our graph, is down. Now, that's the really advanced, I would be really surprised if anyone's actually noticed that. And that's completely fine if you didn't. What I was more wanting to get you to play with, okay, is think about what's this relationship here and how can we use, in particular, either one of these points to start working on that function. Okay. So let's go down and think about method 2 to do this. What we need is g of x is equal to b on x plus 1 plus a. And I need g of 0 to be equal to 3. That's a must. And I need g of 8, like I said before, to be somewhere between 0.25 and 0.33. Okay, I need to be somewhere between that. Okay. Let's start with this. Since we know that's an actual point that we need, and you could go about this problem either way. You could also start by picking a point in here. You could choose 0.3, you could choose 0.25, whatever you want, and choose a specific point. But we're going to start with this coordinate point first and then work from there. So if we know g of 0 needs to equal 3, we can substitute that in. So we're going to get 3 is equal to b on 0 plus 1 plus a. So we get 3 is equal to b on 1 plus a. So we get 3 is equal to b plus a. So we get one equation that tells us the connection plus a and b. And this gives you a point to start trialing values. As long as the two values of b and a that you choose equal 3, you can keep going, and knowing you'll always meet this first requirement. So you might want to try b is 2. Well, that means a needs to be 1. Then you might want to try b is 2.5, and that means a needs to be 0.5. Or you could choose b is equal to 4 and a is equal to -1. And you could keep playing and trialing those until you get our final point, our g of 8, to be in the right area. Okay. So that's one way, and I need to show you a way we can do this in our CAS where we can play with values. We can actually be given a slider. So in this case, let's say we're going to start with b is equal to 2. So we do 2 divided by x plus 1, okay, and then plus, and if we go keyboard, let's put an a there, okay. So I've put 2 as the first bit on x plus 1 plus a, and from here on my CAS, I can actually, instead of clicking the left-hand graph button, I can click this right-hand one. Okay. And this now gives me a slider for A that if I adjust, now your actual CAS won't be as quick because I'm doing this on the computer, but we can see the changes it makes. So there A is equal to 1. What is our value of 8? And we can do a G-solve, and this xcal, ycal is short for x calculation or y calculation, where you put in the other value and it'll calculate what it is. So we want to do a y calculation, put an x value of 8. Okay, it's 1.22222. So that also works. Straight off the bat, that's working. That's giving me a value that works. Because it's through, actually no, I need to be between 0.33 and 0.25, not 1.222. Okay, so we need to be lower. So we could try a 3 there and run the graph. Okay. And we can play with that. Now this is where it gets even cooler, that you'll notice though, as I change this A value, I'm only changing it as the constant on the end and my y-intercept's changing. We've realized that we have this 3 equals B plus A. Or we can rewrite that as B is equal to 3 take away A. So my original function, because I have this requirement here, that requirement means this always has to be true, I can substitute that in here. So let's do that. So we're going to now, we can say that g of x needs to be 3 minus A on x plus 1 plus A. And I can change that into my function here, 3 minus A in the numerator. Graph that. Okay. And currently I had, where was A equals 4? A equals 4, and that's completely the wrong way. So clearly having a negative numerator in that fraction is not good because it's inverted, because 3 minus 4 is negative 1. It's inverted the hyperbola, which is what we don't want. We want a decreasing slope for our slide. So if we put 3 in there, well, 3 minus 3 is 0, so it just makes the whole thing, whole fraction bit of that disappear. Let's put a 2 in there. Okay, we're going through 3, but we're clearly not low enough at when x equals 8. If we put a 1 in there, well, we're getting closer, and we know already from my prior explanation, if we put a 0 in there, we do get the correct answer. Now, if you click on these dots here, we can actually change our slider. So we can change what our min value is. So we might realize we only want to play with values between -1 and 1, and we want a step of 0.1. So we can change those, go OK, and now my slider is much more useful. Okay, but as I change my slider, it's setting my A value, which is impacting the constant term at the end, but also impacting what happens in the numerator. So we can play that way. And then we just keep finding values that work, and that we know 0 definitely works. 0.1, 0.2 looks like it works, maybe. And well, let's see, let's do a calculation. G-solve, we want to calculate at x equals 8, y is 0.155. So no, that doesn't work. Okay, so too low. So we've got a pretty low band for A to actually work, between 1 and point something, pretty small. And then that means B itself has to be pretty close to 3, just a little bit under 3 is the range there. So that's one way to do it. The other way, okay, is a continuation of this. You still would have to do this first point. We know g of 0 needs to equal to 3, which gives us this one equation to solve. And then you just pick a point between 0.33 and 0.255 to generate another equation. Let's say that we want g of 8 to equal 0.3. Well, we can substitute that in to make an equation. So we're going to get 8 is equal to b on x, not 8, other way around. 0.3 is equal to b on 8 plus 1 plus a. So we get 0.3 is equal to b on 9 plus a, and we have a second equation. Okay, and we could call this one our first one, and now we have some simultaneous equations. Okay, we have two simultaneous equations that would meet our requirements. We have 3 equals b plus a, and we have 0.3 equals to b on 9 plus a. And we could solve these either by hand using simultaneous equations, or we can let the calculator do it. So let's do that. Let's go back to main. Simultaneous equation. We've just got two of them. So we've got 3 is equal to, and I'm just going to use x and y because they're the keys that are much quicker to get to. So x is the place of b and y is the place of a. And we've got 0.3 is equal to x divided by 9 plus y. There's our two equations. Put in the simultaneous equation solver, x comma y, and run the simultaneous. So we get from there, so we said x was our b, so b needs to be equal to 3.0375, and a needs to be equal to negative 0.0375, and that meets our requirements. So that would be one way to do it, is when we need to go through multiple points, we can fix one of them and then solve to get a connection what the other one needs to do. So we get this sort of thing and allows us to play. Or we can fix the second one as well. Well, in this case, we fixed it at 0.3 and then use simultaneous equation to solve what our parameters in our original equation needs to be. So there's a couple different ways. We can do it graphically, or we can also recognize through transformations to meet requirements. So there's some examples of how to solve it, but let's go back and look at what the actual question said we need to do. So we need to write a function. Okay. So importantly, function means you'd want to include an appropriate domain, because this one had a domain. We're doing the same thing. Okay. So we want a domain of 0 to 8. We're going to assume that. Include description how you approach the task. So you want to actually talk about why you did what you did, not just show your maths. Like, so I've written down some methods here, okay, but with this I want you to actually write why you did what you did. Doesn't need to be super mathematical language, but you got to describe why. Okay, sometimes the best thing to do with that is diagrams, especially if you're trialing values of a and b. Maybe you try a certain combination, it came up with something, and then you're like, oh, that's too high, so I want to do this. Well, draw a little sketch. Draw a sketch showing that, oh, my hyperbola was too high and I wanted to make it lower. And that's all it needs to be. Okay, I did that, changed that value, but then it impacted something else. So, and you could put made lower, okay? And I did that by translating down, or whatever it is, whatever you made to change. And then, oh, this, I need to dilate some more. Okay, so then I got something else that was a little bit closer. Little sketches like that showing, okay, in this one I set a equals 2, but I need to make it lower, so this was a equals 1, and then this one I did something with b. That's a really good way to show what you're doing. Okay. What techniques did you use? Were you using transformations? Were you using simultaneous equations? Whatever. Do a sketch. Well, I think we all know how to do a sketch over appropriate domain, so you need to have your endpoints, make sure your shape is good. Does your design meet all the criteria? Show that it does or doesn't. So what does it mean to show at currently our level of maths? If I can get the red pen. Show that it does or doesn't. Well, meeting criteria, let's call this criteria 1, 2, 3, 4, and 5. Meeting criteria 1 and 2 is very easy. If your a and b values, just say, let a equal 1 and 1 is between -5 and 10. Done. Let b equal 3. 3 is between 0 and 10. Done. Slide has an initial height of 3 meters. Well, your function's called g of x. Do g of 0, and that should equal 3. Show that the mass actually gives 3. So do a substitution. So substituting 0, and from there, slide has a final height. G of x of between 1/4 and 1/3. Well, g of 8, put that in and show that it's in this range. And the last one, the slope is approaching 0 when the slide ends. So we haven't done differentiation. If you had differentiation, it would be quite easy to do this show. Now, the only other way you can do it is just what is the gradient sort of at that point? Do a rough gradient between 2 points. So we might let's do a bit of a zoom in on the graph. Think about here at x equals 8, and my scale is terrible, but think about x equals 7.9. I could substitute those 2 points in, okay, and get my values and go, oh, the gradient there might be negative 0.03 or whatever it actually happens to be, but it's really close to 0. So find the gradient between those 2 points that's near the end, and you can make a comparison between what the gradient is at the start. You could do how you could even go between 0, x equals 0 and x equals 0.1 and show the gradient there is steep. That might be m equals -1, and at the end it's m equals -0.03. You can say the gradient is getting closer to 0 and the actual value of it is quite close to 0 at the end. Would be the way to go about showing that one. So a little bit more work involved in that last design point. Yeah, so a lot of the work, once you've even found, like, there's a lot of trial and error work or simultaneous equations or whatever, but once you've done that, is then actually breaking down and addressing these criteria. Want to see you working and your thinking. But that's it. If you have any questions, as always, stick them in the comments below or on Google Classroom. Thanks and see ya.